Now we have a presentation from Zhang, and the title of the presentation is Self-Auxiliary Distillation for Simple, Efficient Learning in Google Scale Recommenders. Oh, we have two speakers. Okay. So, welcome. The stage is yours.
Good afternoon, everyone. Ying and Ruoxi here from Google DeepMind. So we're actually very happy that the keynote from Michael Jordan earlier today talks to the importance of the work we are going to share with you all. I think most of you here work on recommender systems. Maybe you have noticed a recent trend in industry where there is a significant signal loss in conversion labels caused by tighter privacy controls. And that has led to increasing difficulty in training more accurate models and consequently worse user experience. And our talk will share you with the journey we have to fight this signal loss problem. So let me first give an overview of the larger data efficiency landscape. On the one hand, we have lots of data, for example, impressions, clicks, and even people in this room who are using the phone are creating lots of data for the past hour. But is it a good idea to use all of them? And we have a poster that answers this question if you're interested. And on the other hand, we have extremely sparse data. For example, user evaluations, conversion labels, co-star items, creators, and users. And this talk would focus on a subset of this sparse data regime, which is conversion signal. So the problem we have is that it's becoming more difficult to train accurate models because of the conversion signal loss. Conversion signals are highly valuable because they often involve user decision-making. For example, how many of you have downloaded some local Italian taxi app this week to just get around the city? And would you do that if you want to visit in Italy? And you see, there is always this intention and decision-making behind these conversion signals. And that's why they are so valuable, much valuable than clicks, which could be very random. And that's also why that they're super sparse by nature. And what's worse is that they're becoming much more sparse and also biased because of the tighter privacy regulations. So now, with very limited signals, how can we make better use of them? And the key insight we have is that not all the labels are created equal. Some are of much higher quality, but others could be very noisy and random. For example, for the conversion signals, the positive ones are of higher quality because they often involve user decision, but the negative ones could have a completely different story. There are so many false negatives. For example, you're planning your trip to Italy, and you're browsing online and saw this very nice leather bag. You were tempted, eventually you purchased it. But this purchase conversion may not be reported because of the privacy regulations, or we simply missed it because there has been so much time in between the two events. So there is actually a spectrum of quality around these positive and negative labels. So we should really try to differentiate these quality of the positive and negative labels in our training process. And in the next, Ying will talk more about the technical details.
Thanks, Ruoxi. So to train the label differently in the modeling, there are several challenges. First, how to stabilize the model calibration. If we treat the label differently, it's easily to cause the model over-predict or under-predict issue. So how could we address this problem in the modeling? Second, how could we use the high-quality labels and the low-quality labels, and how could we identify them? Third, how could we find a scalable solution that can be used for most industry scenarios? And we also want our model to be highly scalable for industry-wide usage. So to address those problems, we propose a novel technique called the self-auxiliary distillation. The whole framework are shown in this figure. It contains 3 parts. So the main task, auxiliary task, and the shared part. So for the main task as shown here, it trains on the original labels and used for serving, and the output also used for the teacher predictions for the auxiliary task. This is used to maintain the model calibration. Here, the calibration will mean to make the model serving predictions to be the same as the ground truth label, mean label. So the second part is our introduced auxiliary task. It trained as the student that distilled from the teacher predictions shown in the yellow color and also the ground truth labels. This is a core part of our proposed self-auxiliary distillation work, and I will give more details later. And the third part is shown in the gray color. It's the shared DNN tower and the feature embeddings. By using this sharing part, the learned gradient from the auxiliary task can be shared and transferred to the main task and final benefits the serving predictions. So concretely, for the auxiliary task, it has a bilateral branch. The teacher branch contains the high resolution for the low quality labels that are learned from the main task, shown in the yellow color. And the ground truth branch contains the high quality labels that is from our ground truth data. Then a selector is used to automatically select the 2 different kinds of labels in a flexible way. For example, in practice, as Ruoxi mentioned, for many conversion models, we find most positive labels are very important. In this situation, we could use the max of the ground truth labels and predict labels as the selector for this auxiliary task. And also, we could use other functions for the selector, like the minimum or even the curriculum learning, to optimize the auxiliary task learning. So for the experiment, we evaluate our self-distillation on 3 Google platforms, and we found they are consistently improve the model performance for both offline and online. And through the various ablation study, we find the mixed labels in the auxiliary head plays a pivotal role to boost the improvement. More importantly, we find that the self-auxiliary distillation surprisingly works well for effectively mitigate the Apple iOS app tracking transparency policy. And it gives a huge improvement for these severe signal loss challenges. So the self-auxiliary distillation already be launched over 3 Google major products, and it is highly scalable with negligible training cost and no actual serving cost. It also addressed the severe signal loss challenges, as Ruoxi mentioned. So here is the key takeaways. We proposed a self-auxiliary distillation for the recommender self-improvement technique. And the mixed labels gives a high improvement for the models. The auxiliary head offers flexibility to train on diverse labels and data without hurting the model calibration. Thank you. Questions?
Thanks. Thanks for your presentation. I have a curiosity, a question. It's not clear to me if your self-auxiliary distillation framework has been designed mainly to manage the huge amount of data and signals of, let's say, for scalability, or if the main goal was to address the signal loss problems with, for instance, Apple policy. So, which was the main goal?
Yeah. That's a great question. So this self-auxiliary distillation is a general framework that can be used in different scenarios. And we find this technique plays very well for those signal loss problems. Like it gives more improvement under the signal loss settings.
Okay, thanks. Thanks again. And we can thank the speakers.